Chat messages. Yeah, yeah. Thank you so much. Let me take out this presentation separately. And yeah. So Sachin sir, please help me if there is any questions or anything, any technical problem. You can just unmute and tell me. Or if there is, if I got disconnected, just give me a quick call. I'll
Sure.
reconnect back. Huh?
Sure.
Okay then. Thank you. Thank you. So there is a small change in the plans. Like I hope people have already informed. Dr. Anindita got busy, and our session of 1 hour is moved to some other session timing, which will be informed soon. So I'll be taking both these hours today. So sorry for the delay. So it was like suddenly planned. So I just like landed in Hyderabad. I'm in the launch, so I'm presenting decisions from there. Please bear with me if there is any issues. Okay then. Yeah. So what you can see here on the first day we started with why do we need to go for quantum computing when we have classical computing doing fine. So that is the time people were trying to study the biological processes, which in fact involves the quantum physics rules or quantum physics based dynamics. Actually, they are to study them. We better use uh, something called a machine, which is based on quantum physics rules. Okay, so people took that idea and then followed it up, designed a quantum machine, and even came up with the quantum algorithms, which are very powerful. So, like Shor and Grover, we saw that. Okay, and then we went on to discuss about how qubits are realized on a classical device, right? Okay, so on a classical device, qubits are realized using alignment of particular atoms' magnetic moment. You see here, okay? The magnetic moments are aligned. If I just take a material which retains its magnetic moment after I align, it remains the same. Just like kids, when you teach them, they're good kids. They take the idea like whatever concepts we have told. So they just use that for future. Same way. So if you just take a ferromagnetic material, when I try to align their magnetic moment, they remain the same. So they use a particular region to represent 0 bit and 1 bit. So in that way, classical memory is being realized. When it comes to quantum memory, so people started playing with a single atom, not many atoms. So when you start manipulating the atom, let's say inside the atom, there is a valence electron, outermost electron is there. When you try to push that electron outside either atom or the next available orbit, we need to supply energy in the form of some photons. When you supply photons, it might observe, it will not observe. That is becomes probabilistic. Why the probability comes? Because of the things are so tiny, there is no certainty at that level, okay, at a quantum level. And the uncertainty is coming because of the even particles behaving like a waves. Okay, so the waves would exist everywhere. In the same way, particles would exist everywhere because of their wave nature. And how should I know their location or a possible probability location? What I do, I take the probability like a wave equation and take absolute square of that. Wherever there is a peaking, that is the point where I would get the maximum possible location of that particular particle. Okay, right? So in that way, you can just see in a 3 dimension and find out where is the particle it can be existing or where the particle do not exist. If you see where there is a hill, there is a wave peaks. This is called a wave maxima and this is a wave minima. And so crust and trough they call. Wherever there is absolute square of a wave equation is going to be 0, you can certainly say electrons or particles of quantum nature do not exist there certainly. But everywhere else where there is a non-zero absolute square of a wave equation, there will be a chance of electron can be formed. Remember, if I just put an electron in just a one-dimensional box like this, it can exist in this wave nature, it can exist in this nature, it can exist in even this nature. We don't know. It can exist in combination of all these three natures. I just showed only these three cases. There will be infinitely many possible cases. Okay. I can do one thing. I can just confine the electron to, let's say, only in the state of n equal to 1 and n equal to 2. Or I can only confine n equal to 1 case. Okay. So that is by just from external means I can supply some energy and tackle that. Okay. Right. So if I take the same particle in a box in 3 dimension, the wave equation, the dynamics of the wave equation is represented by this Schrodinger equation. We are not getting into the details of the Schrodinger equation. Probably somebody who is interested can get in touch with me. I'll just help in understanding this one. It is just like, remember, there's a simple equation. It's just like Newton's second law, force is equal to mass into acceleration. That is a simple. The equivalence of this Schrodinger equation in a classical dynamics is just Newton's second law, where there is a force is acted and which moves a particle of mass m with some acceleration. Particle, not I'm not saying particle, a box or something, an entity of mass m will be moved. So here you see the E is there, which is the energy with which a particle can exist in. For example, here the energy corresponding to this wave nature is 1. Energy corresponding to this is another value. Corresponding to this is another value. So there are wave functions, means system can exist in various wave functions. Corresponding to each wave function, there is a particular energy associated. Okay. So that is what you see. E is the energy, right? And psi is a wave function. Planck's constant is there. Mass of a particle is there, and there is a U. U is like potential. Potential in the sense, if you just take a marble in the small marble inside a dish, a vessel, within that vessel, particle would exist. It moves here and there. Okay, it is just like that. Or you just take a pendulum, take an oscillate. Pendulum is existing in a potential of potential dictated by a thread and also gravity. So here U is like the environment in which the particle is existing. Okay, it's called potential. For example, in this case, it is actually inside of one-dimensional potential. The potential is 0. This is a particle in a box. Inside that, potential is 0. Right side, wherever L is x is greater than L or x is less than L, potential is infinite. Okay, that means it is just like a very long high wall is there. If you put a particle inside, particle cannot go left or right. It is confined within. Where it is confined, it is existing within a zero potential. There is no energy. Okay, so if it is something like you put up a person inside about one-dimensional wall, to cross to the other side, he has to take energy, get some energy, and like climb and go out. Okay, some even in quantum computing, there is a chance even without energy, particle can tumble through, right? It can just say something called tunneling through this walls. That is another domain of understanding one has to use. But as of now, you can say U is dictated by whatever environment which you are considering in the particle system. Okay, right? This is the differential equation of second order in space, right? And if you solve this differential equation, see here you am putting U equal to 0. If you solve this differential equation, in fact, if you see when you substitute U is equal to 0, this entire equation becomes just a second order differential equation, and also it is become linear differential equation. Okay, so that means beautifully it possesses sinusoidal solutions both in x, y, sorry, not in both, all x, y, and z direction. Okay, so you can get what is the functional form from the Schrodinger equation. Okay, the wave for the wave. So which is a nice sinusoidal wave. That is what we were plotting in the first place. You see, then so how did I get the sinusoidal wave nature for a particle? That is actually solution of a Schrodinger equation. It is sinusoidal in x direction, y direction, z direction. Okay, and with what energy it gets, it is sending a disturbance of wave. With what energy? You can also calculate from the Schrodinger equation itself. Okay, because if you just see this wave equation, it is only exists between x equal to 0 to x equal to L. Wherever there is x equal to 0, wherever there is x equal to L, the Schrodinger equation, wave equation actually vanishes. Means it is confined, which means particle should not exist anywhere at the boundary. On the boundary, it cannot exist, right? Next to the boundary, it can exist. Using that initial boundary conditions, just like any boundary condition for a differential equation, this is second order differential equation. I can put in the boundary condition for psi going to 0 at x equal to 0 and x equal to L. I can find what is the corresponding energy values. Interestingly, what you find is this expression where L is the distance, okay, within which it is confined, okay. For 3-dimensional it is showing. If you want to 1 dimension, just ignore the next 2 terms, where n corresponding to the orbit number, you can say. This is the first orbit, second orbit, and third orbit, and so on. So a given particle can exist in multiple orbits with particular probability. Okay, remember that. Fine. So if you just take this expression of psi, and when you plot, okay, with respect to x, y, and z, this is what you see: nice blobs around the nucleus. You see nice blobs. This is what you see: orbitals of a hydrogen atom. See, nice picture. There is a nice video from this minute physics on Google. You please explore that. Okay, we saw that. And since that probabilistic nature is there, people thought, why don't we pick any 2 points or 2 possible locations, right? And confine the particle to those 2 possible locations, particle in the sense electron here, and realize a memory out of it in terms of the probability numbers as such. Okay. So we saw how Dirac helped us to describe a wave function in terms of probability amplitudes, where alpha, beta are probability amplitudes, and then actual probabilities you can arrive by taking absolute square of that probability amplitudes. Okay, fine. So in fact, when you try to write that Schrodinger wave equation in terms of 0 ket and 1 ket, it appears just like a 2-dimensional vector. If I confine the vector to be unit length, so it becomes a unit circle. Okay, right? And then we saw that there is a very good resemblance between the basis of 2-dimensional vector space and the basis of vector, quantum vector, which I wrote, or Dirac wrote, in terms of 0 ket and 1 ket, where 0 ket and 1 ket are the basis. Okay. Since they are resembling each other, they should also satisfy the properties. Then only I can call a quantum state a vector, right? So what would be the operations between the basis elements, you could ask? So simply, right, there may be some product agar exists between 0 to 0 ket, which should give me 1. 1 to 1 should give me 1. 0 to 1 should give me 0. So what it could be? So Dirac thought that, why don't I introduce some matrix notation for a 0 ket in terms of a column vector 1 0, for a 1 ket in terms of 0 and 1. The moment you introduce, you see 0 ket is actually created out of a vertical line, a 0, and a right angle. It is a column vector. So column vector, if we take a transpose of it, it becomes a column, a row. Okay. So similarly, ket of a transpose of a ket is a Bray, and the corresponding matrix representation is a row vector 1 0. So interestingly, the matrix multiplication between 0 to 0 ket is done by taking the left hand entry of that product and take that and take a transpose of it, and it will become left angle 0 vertical line 0 right angle. Together it is called a bracket. So if I do the matrix multiplication beautifully, a column, a row multiplying onto a column gives me 1. Okay, right? It gives me 1, right? Yeah, just a minute. Huh? Okay, yeah, fine. So fine. So I can cross check everything else. I asked the participant even to cross check. So interestingly, what I have is, if I have a quantum state like this, okay, ket notation, I can also write a ket notation for quantum state psi ket as alpha beta. And for a Bray psi, it's a row vector alpha beta. Remember, I forgot to mention alpha star beta star here. I simply said transpose earlier. In fact, it is not just a transpose. If I alpha and beta, if I choose them to have a complex number, right? If I choose them have to complex numbers, in that case, what happens? Alpha star, beta star, I should use for a Bray sign. Okay, right? So all the quantum states which we were going to use in quantum computation would involve complex numbers. So when I take a transpose, or if I try to convert a Ket notation to Bray notation, what I'm doing a transpose. Also, I'm doing complex conjugate. So from now on, the Ket to Bray is actually not just a transpose. Transpose plus complex conjugate, it is actually represented by dagger. Also, it's called adjoint of a matrix or adjoint of a column matrix. Okay, right? So there is a geometrical interpretation for any quantum state here using a block sphere, which is in fact the upgraded version of a spherical polar coordinate system where r vector or r dimension is being reduced or removed by confining r equal to 1. In that case, I'll have only two dimensions. One is theta, which measures from vertical z-axis, from z-axis to the negative z-axis. So where theta goes from 0 to pi, and on the horizontal surface, that is the equatorial plane or any plane above or below equatorial plane, it's just like if I take an apple and chop it horizontally, on those plane, the phi is going to vary between 0 to 2 pi. Okay, so what people have done, or Dirac has done, he deduced alpha in terms of cos theta by 2, beta in terms of exponential I phi sin theta by 2. The moment you do that, any point on the surface of the sphere would correspond to a quantum state. Interestingly, the north pole, the north point, would correspond to theta equal to 0. Is a zero ket state. Means if I somehow confine the electron to just a ground state, I would have that represented on a block sphere on a north pole. If I confine the atom to the excited state, which means I have run the theta from 0 to 2 pi, okay, in that case, I'll have quantum state confined to the south pole. Remember, exponential I phi, the term is not going to play any role when I am talking about a single point on the north and the south, because the single point, there is no variation in the horizontal plane. Anywhere else, if you just take, you will have a disk. So there, the phi is going to make a big difference. Okay, so there are particular scenarios when I have theta is equal to pi by 2. When theta equal to pi by 2, you see, along the x-axis I'll get a 1 point, along the y-axis I'll get a 1 point. Correspondingly, if you substitute theta equal to pi by 2, you would have 1 by square root of 2 here, 1 by square root of 2 here, and now there is a chance of phi taking multiple values. When phi takes a 0 value, I'll have 0 ket plus 1 ket divided by square root of 2, which is along the x-axis. When phi takes 90 degrees, then I'll have exponential I pi by 2, means it's a I vector or a iota. I'll have that iota here. So what you see here is along the x-axis on the surface, there is a superposition of 0 ket and 1 ket with equal probability. You see, 1 by square root of 2 is a probability amplitude, and probability would be 1 by 2. Similarly, even here along the y-axis on the surface of a block sphere, you have 0 ket and 1 ket equal probability. Why? Because the probability amplitudes may be different for 1 ket, which is 1 by square root of 2. In the case of here in this case, it is I by square root of 2. When you take absolute square, I is not going to contribute because it's going to become 1. Okay, right? So higher dimensional quantum system, how I am going to do? I just take two atoms and combine them, right? Physically, I am going to combine them, right? And literally on a paper, it is actually tensor product of their particular quantum state vectors, which are represented in a column notation. Okay, so beautifully I can have for using two atoms together or two quantum systems of two substates. If I combine them, I create a four substate quantum system, which is 4D quantum basis. Okay, so I can keep on going. I can enlarge as much as size I want. I can go for it. Okay, so this is where we left off, right? So we will start today a single qubit gates. Okay, so let me see if I am there. If there is any issue, sir, use the whiteboard better to understand. Okay, yeah, but I'm trying to connect. Uh, okay, I'm trying to connect my tab. So it will take some time. That's why I'm not doing it. Okay. Yeah. Anyway, I'll use in the second half. Don't worry. I'll use and I'll show you. Right. Okay. So now, yeah. Wait a minute. Mm. So if you just think about quantum systems, which are quantum states now, okay, right? Now those quantum states are there. How should I process the quantum state, right? In the classical communication, if you see, right, how do you process the quantum state? You sorry, classical information, classically in the classical computation, you just go simply, use some gates, okay. So the gates are like the initial gate, which we usually think is a NOT gate. What it does is it just converts NOT gate. It converts a bit. If it is a high bit, it converts that high bit into 0 bit. Okay, 1 bit converts into 0 bit, and 0 bit is converted into 1 bit. That is a NOT operation. We also call that a negation. Okay, so we call it the negation. So the question is there a such gate in quantum computing? Right? Of course there is. That is, again, you can say it's a quantum NOT gate. Okay. So what it does is it takes the quantum state into it. Okay, and converts that quantum state into, see, 0 ket becomes 1 ket, 1 ket becomes 0 ket. So which means, right, what happens? My quantum state, right? Uh, 1 minute. I'm just trying to connect. One minute. I'm just trying to connect my whiteboard. Okay, I think I'm connected. So let me log in. Mm, just to give me a minute. Only a minute. Yeah. So here in this case, a given quantum state, right? 0 becoming 1, 1 becoming 0. If you just see, let's say I got a new quantum state, which I'm calling it as, let's say okay, let's say it is some new state. Okay. QT, QCT, 1 minute. Huh? Yeah. Right. I have connected my device. Right. Okay. And
Are you sharing another screen? It is showing.
I'll just share another screen.
Okay.
I'll just share another screen. Share the content. So should I keep this? Earlier, I used to do everything with the one laptop, which is a touch screen. So it was easy. Right. Okay. I'm able to see. Wait a minute. Okay. Can you guys see me? Yeah, I think you are able to see. Okay, perfect. Okay. 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 So let me say Google Notes. Right. Okay. Let me say new notes. Yeah. Okay. Right. Right. Yeah. So if you see, there is a quantum state which is a zero ket. Okay. Right. So how should I process that? I want to. This is zero ket should become one ket. Okay. So one ket is what? What is this column representation? It is 0 and 1, right? So I am starting with this 0 ket. I want to convert that to 1 ket, right? If you see, this is a matrix, and the second one is also matrix. It's a column matrix, by the way, which means the transformation happening from 0 ket to 1 ket may be as a matrix multiplication, right? So that means I will have some matrix which will have 4 elements, which ensures transformation of 0 ket to 1 ket. How? Very simple. By trial and error method, you can also think about it. Okay. So by trial and error method, I can say if I have a quantum or a gate, a matrix, something like this, 0, 1, 1, 0, and if it acts on 1 ket, 0 ket, if you see, the output is, okay, the output is simply 0, 1 multiplying onto, okay, 0, 1 multiplying onto 1, 0 gives me, okay, gives me 0. 1, 0 multiplying onto 1, 0 here gives me 1, which is what? In fact, it is 1 ket. Okay, so that is interesting. So the matrix which is doing transformation from 0 ket to 1 ket, let me call it as some X gate or X matrix. Okay, so this is the X matrix, right? So X matrix, that's conversion from 0 ket to 1 ket. When you just go back and see in the notes, what did I showed is I started with a quantum state psi, which is having alpha 0 ket plus beta 1 ket. When I do the transformation using X gate, I would be getting quantum state psi prime, which is actually alpha 1 ket plus beta 0 ket. So what is happening there is just the probability amplitudes are actually getting changed. Okay, so the probability amplitude, if you just see, so if I just rearrange my new quantum state, okay, new rearrange for my comfortability, what it is beta 0 plus alpha 1, right? So that means if you see, alpha goes to 1 ket, beta goes to 0 ket. So that is what the X symbol you can understand, you can remember. It's a X gate. Okay. So interesting, if you just take a X gate or a matrix X, you multiply with itself. Okay. So what you get is identity matrix. Okay. So what it means, if I just take a matrix, multiply it to itself, even though you just take, let's say you just take a joint of that, because I can't just multiply just for the for the time being. Just take, you get identity. Okay, so this kind of a property in linear algebra called unitary matrix. Okay, it's called unitary matrix. So you can just straight away say, right? So in quantum computing, the first gate is a X gate. It's called a classic, sorry, it's called a single qubit gate, which transforms 0 to 1, which is like 0 to 1. And if you act on 1, it will convert to 0. Okay, right? Since quantum state doesn't have single bits, if a single bit is 0 bit or 1 bit, if you just say it is a classical bit, it's a classical. But in quantum systems, we always have a superposition, right? We always have a superposition. Then only I can say it's a quantum state, right? So quantum states goes through a X gate or a X operation becomes again some quantum state with same equal probability, but probability amplitude may gets changed. Okay, that is most important, right? Fine, I have no X gate. What else I can think of, right? What else I can think of? First thing is I just interchange the, just take a quantum state. The first operation I can think of is interchange their probability amplitudes. Okay, so that is done by X gate. The next thing is, let's say I have, let's say I have a probability amplitudes. I want to fiddle with the probability amplitude. Okay, what is fiddling? What kind of fiddling I want to do? I have a alpha 0 plus beta 1 I have. What kind of fiddling I can do? See, interestingly, the signature of alpha, the sign of alpha is positive, sign of beta is positive. Is there any way I can introduce some change in this parity? Okay, right? Uh, right? Is there any change in the parity I can do? Of course, there is a possibility. Let's say I want to convert plus to minus sign. So what I mean is the quantum state in its column notation appears to be alpha beta. Okay. Let's say I want to convert that to alpha minus beta. I want to introduce some kind of a phase parity between the probability amplitude. Remember, the quantum state may remain the same, but the individual probabilities are just going apart. It's a the zero kit is going in one direction, beta is going in another direction. It's completely out of phase, like 180 degrees out of phase. How should I do that? Okay, so interestingly, how should I do that is if you just take a quantum state, okay, alpha 0 plus, if I introduce some I 5 beta 1. Okay, or if you are getting confused, you can put a theta here. I want to introduce this exponential I theta, okay, for the quantum bit state 1 in such a way theta is actually pi. I want to introduce that. How can I do that? Okay, so as we see, the quantum state representation of this quantum state, like column representation of this quantum state is alpha beta. I want to introduce exponential I5 for beta. So what should I have? I want to have some matrix multiplication, which should not do anything with the alpha. So I'll just put a 1 0, but it should do something to beta. What is something it has to do? It has to introduce exponential I pi value. It should multiply to beta. So I can simply put a 0 exponential I pi. If you multiply it, like definitely you are going to get alpha exponential I pi and beta, which is in fact equal to alpha minus beta. Sorry, exponential I pi is minus 1. So minus beta, right? So if somebody is getting confused, what is exponential I pi? So you just see exponential I theta is actually cos pi plus I sine pi. Okay. So sine pi is 0 anyway, it is not going to contribute. Cos pi is minus 1. That is what this minus sign we are getting. Okay. So you can straight away guess what could be a quantum gate which introduces a phase change or a parity change to the individual probability amplitude. So that is simply called a Z gate or a Z matrix. Okay, so which is 1, 0, 0, exponential I pi is 1, sorry, minus 1. Okay, so this is a gate for you which induces a change in the parity only for one gate. Remember, if I act a Z gate onto 0 gate, it will not do anything, it just gives as it is. Okay, if you just take a Z gate, act on 1, it will convert the probability amplitude of 1 to something minus 1. This is what you get. Okay, so that is very, very important. Z gate or a Z operation only has effect on the one gate, right? So far we saw X gate and the Z gate, right? So what else you can think of, right? Okay, the single qubit gates which we are thinking as of now, right? So we were talking in terms of creating a superposition, right? Okay, so creating a superposition means I want to have a superposition of alpha 0 ket 1 ket. Okay, so okay, let me say, yeah, take a quantum state. Maybe I'll write down separately. Okay, let's say I have a quantum state in a 0, which is single bit state. It is in a classical bit, which means if I just two level atom, if I just take, if the electron is strictly confined to the ground state, okay, it is not possible. So you can do absolute zero temperature. You can surrounding temperature, you make it to absolute zero. So for ideal situation, you can think it is in a classical state. Okay. Now it has to become a superposition state. What is that superposition state? Is alpha 0 plus beta 1. This is the arbitrary superposition state. Means we don't know with what probability it exists in the ground. We don't know with what probability it exists in the excited state. Okay, right? So how should I go from here to here? Okay, so in fact, what is this state physically mean is, in fact, if you just see, at a given point, it exists with a probability amplitude alpha in the ground, probability amplitude beta in the excited. The corresponding probabilities are alpha square plus beta square. No? It is just like the electron is doing a hopping between ground and excited continuously. That is what the superposition means. If you just take a coin, just to toss a coin, during the flight, it exists in both the excited and like a tail and head state. That is what you see 0 ket and 1 ket. That is what the superposition is. Okay. So how it is achieved is physically in the experimental lab. Okay. So people send a stream of photons, not just a single photon, many stream of photons. Okay. A pulse of photons they call. So many photons are there. Wait a minute. So one photon, second photon, third photon. So which is a collection of many photons. It is in the pulse. So this pulse will go, so interact with the atom, which is only as of now in the ground state. Okay. What happens? The first photon comes, puts the electron on the excited. It can't exist there forever. It will comes down. By the time it comes down, another photon will come, knocks the electron out up above. It goes to up. Again, it comes down. So, in fact, it is doing a hopping between this. It is just like you go to a park, you just create a swing which is oscillating continuously. Whenever it tries to stop, you are going to push again in such a way that in a in synchronicity, in resonance, you will push. So the hopping happens between ground and excited, uh, right? 0 ket and 1 ket. Okay, so supplying a stream of photons or a pulse of photon is actually putting the photon electron in a strict ground state into superposition state. Okay, so physical experiments we just saw, right? Experimentally, that is the situation, right? So if I want to represent that, okay, if I want to represent that on paper, how should I do that? Okay, so on paper, if you see, let's say I'm starting a quantum system in a strict zero state, 0 ket state, which means 1 0. Okay, which should become a superposition state. Let's say for time being, arbitrary superposition alpha beta. Okay, right? For for our convenience, let's take alpha equal to 1 by square root of 2, and that which implies beta is also 1 by square root of 2. So the probability amplitude is alpha, and both beta square is just 1 by 2. There's a 50% probability. So how should I create a quantum state 0 ket to superposition state? So physically, I know I send a stream of photons or a pulse of photon onto the atom, right? So that will put a superposition. On paper, what is the corresponding quantum gate or a quantum matrix? A matrix which is, let's say I don't know that matrix. For the time being, let's say I have my input quantum state is 0 ket, output is, let's say I have 1 by 2 square root of 2, 1 by square root of 2. Okay, what is this corresponding? What is this? What it will have? What elements it will have? Okay, so by trial and error method or some other technique you can find which is actually corresponding to 1 1 1 minus 1. Okay, if you have this 1 0, if you multiply, you are going to get 1 1. Okay, and there is a denominator, some some number is there. So just to see, I want to avoid the new quantum state form should be a unit vector. So this is not a unit vector. Okay, it is a vector is having more than one length. So what I need to have, a matrix need to have 1 by square root of 2. If this is I have, I'll get, interestingly, 1 by square root of 2, 1 by square root of 2. So this is a matrix which creates a superposition from a single classical bit state. Okay, right? So you can also cross check, you can cross check later on. Okay, right? So I think it is okay. Let me take one more notebook. I'll just say one. Okay. Yeah. New drawing. I'll take new drawing. Okay. So now you take one more. Let's say the matrix I have 1 by square root of 2. Just a minute. 1 by 1 by square root of 2. Okay. Let me draw a bigger one. 1 by square root of 2. 1 1 1 minus 1. Okay. Let me clear this. Okay, this is the matrix I have. So people name this as a Hadamard matrix represented with a H. So interesting property of this one is puts a single bit state to superposition state 1 1 with equal probability. Beautiful, right? Okay, so you just take a Hadamard matrix once again. You act on one ket. What would be the output? Okay, so interestingly, let me give the output state which looks like 1 minus 1. Okay, what is this is? It is equal probability of 0 ket and 1 ket, with 1 ket being opposite parity. That is the effect of Hadamard gate on one ket. Okay, so in both the cases, whether you start the atom, whether in the ground state or in the excited state initially, you act a Hadamard gate, it is going to create near superposition. Only thing is the priority or there is exists out of phase between 0 ket and 1 ket in the superposition state when corresponding to the whatever initial state, whether I'm starting with initial state 1 or 0, would dictate what is the parity between or the relative phase between 0 ket and 1 ket. Okay, so again, now what is the specific properties of Hadamard gate? Earlier we saw you take a X gate, multiply X gate with its adjoint, I will get identity. Okay, I may not have said, but even for Z gate also, if you try to do, you will get identity. So which means even it should satisfy with Hadamard gate also. No? You can cross check. Definitely, it is going to satisfy. So which means all three gates are unitary by nature. Okay, so you can say now there is a chance that unitary gates any unitary gates could be represented by, or any quantum gate could be represented by unitary matrices, or you just take any unitary matrix, it may have a chance to become a quantum gate, but is not is given, but other way around it is given. Okay, so these are single qubit gates, right? So in a way, it's a combination of these individual gates. You can also come up with a new gates. Okay, so between x and y, like there is y gate is not there, is the question, right? You can ask. Of course there is. Okay, so y gate. Okay, interesting property of y gate is it does it creates the effect of x gate and also z gate together. It is like all rounder. Okay, so what it does is, if you just take a y gate specific representation, let me give that. It is having minus I. Okay, I 0, I r 1. I'm sorry, so is 1. Okay, so this is a y gate representation. So just to see what is the action of y gate on 0 hit. Okay, so let me do that. 1 0. Okay, so what I'll have, 0 minus I multiplying onto 1 0, I'll get a 0 here. 1 0 multiplying onto 1 0, I'll get 1. So what I'm getting is, I'm getting 0 becoming 1. What is the effect? This is the effect of X gate. Beautiful. So whenever I take a Y gate act on 0, I will have a effect of X gate operation, means 0 becoming 1. So let me cross check. What about for 1 ket? Okay, what is the action of Y on 1 ket, which is 0 1? Okay, now 0 minus I multiplying onto 0 and 1 gives me what? It gives me minus I. Okay, and 1 0 multiplying onto 0 1 gives me 0. So let me rearrange this as minus I 1 0. Okay, so what is that? Minus I 1 0 means 0 kit. Okay, so what it is doing, interestingly, you see, it is doing 1 ket converting into x, sorry, 1 ket becoming to 0. It is an action of x. Okay, and also y acting on 1 gate's superposition, sorry, the negative phase with a minus I. Okay, which is like a action of z multiplying with I. Okay, so that is why I said y gate is an action, is a combination of x gate and z gate with some I extra factor coming in. So y is also a gate, a possible gate which does the action of both x and y, x and z. Okay, and one more thing, you can cross check whether y dagger is going to give me identity, which is whether y is a unitary matrix or not. If you can cross check. Of course, this is a unitary matrix, so you can just confirm it as a unitary gate. Okay, so the list of gates which we have saw so far is a X gate, a Y gate, and a Z gate, and Hadamard gate. All are single qubit gates. Okay, right? Single qubit gates. Fine. So the property of the single qubit gates, X, Y, and Z, they are actually either shifting quantum bits, single bit state to 0 to 1 or 1 to 0, or taking extra, adding a phase of minus 1 or not, something it is doing. Sir, can you repeat what is the action of Y gate? Okay. So Y gate, if you see, okay, let's say I have a matrix like this. Okay, 0, minus 1, 1, 0. If I take that matrix Y, acting on 0 ket is going to give me 1 ket, okay, which is the action of X gate in the first place, which we saw. You take the same Y gate, act on 1 ket. What I am getting is minus I multiplying to 0 ket. So it is doing action of X also, and also it is doing action of Z also. Z action on a 1 is adding a minus I, na? Okay? So minus 1. So that it is doing, but it is multiplying with the extra factor of Y. Doesn't matter. So we are trying to see both X and Y action, or X and Z action on the bit state when I choose Y. Okay? So together, X, Y, and Z are actually they are the Pauli matrices. If you just take Pauli matrices, the physics people may be knowing Pauli matrices are like this: sigma y 0 minus I 1 0. Okay, sigma z is 1 0 0 minus 1. So the interesting properties they have. There is a linear, there is algebraic relations between Pauli matrices. So you can also call the X, Y, and Z gate as a Pauli gates. Okay, and only the H gate which is actually deviating from the nature of those gates which we saw. Okay, so what is the nature of this gate is it starts from a classical bit state, create a superposition state. It is just like supplying energy to the atom in the form of pulses. Okay, right? Okay, in Hadamard gate, ensure equal probability of 50-50% of measuring 0 and 1. What about the phase difference, sir? Okay, so the see when I have Hadamard gate acting on 0, I'll get 0 plus 1 with equal probability. There is no relative phase difference between 0 and 1. Okay, but if I take a Hadamard gate, act on 1, I am going to get a relative phase between 0 gate and 1 gate. So Hadamard gate only creates a phase difference between 0 and 1 when I initial state, if I'm choosing on which the quantum gate H is going to act, which is going to make a lot of difference. If I initial state is 0, no phase difference. The initial state is 1, there is a phase difference of minus. Okay, right? Fine. So Hadamard gate, which just saw, right? So the next thing is, okay, 1 minute. Yeah, I'm just trying to see my notes. Are we on the right track? So you can cross check whether Hadamard gate is unitary or not. Okay, you can cross check. Of course, it's unitary, right? Okay, right. Now, so you see in all these three gates, interesting properties. Okay, so you take a block sphere. Okay, horizontal equatorial plane is there, z-axis is there, x-axis is there, y-axis is there. Okay, so initially quantum state is 0. When I add the x gate, so quantum state is pointing towards the North Pole. When I add the x gate, what happens? It is going to create a one catch. Okay, so what it means is the X gate is actually rotating a quantum state from North Pole to South Pole. Okay, so in fact, X gate is like an operation which rotates quantum state by angle phi 180 degrees from north to south. If you start from, if you just start from 0 ket or 1 ket, X acting on 1 ket pushes to 0 ket. Now, so which means 1 becoming 0, right? So even in that case also rotation is done by 5 degrees, 5 radians, I'm sorry, 5 radians. So you can say X gate is an operation on a block sphere rotating a quantum state from north to south pole. Now when you talk about the rotations, it should be about some axis. Okay, so here rotation you can choose, it is about a x axis. Okay, fine. Now that is what we saw. Now let's take about Z vector. Sorry, Z gate. What Z gate does is it acts on 0, gives 0 itself. Z gate acts on 1, gives minus 1. So how should I have that effect here? Okay. So in fact, okay, when on the block sphere, Z gate is not going to change the quantum vector state 0 or 1, but it is going to add a phase change of 180 degrees. It is going to add a phase change for one ket that we are not able to show on a block sphere. We will see. I'll just show you some demo quickly on a quantum IBM quantum experience. Okay, so Z gate I can't see. Okay, and Y gate also I can't see, because what is the effect of Y on 0? It should become 1. What is the effect of Y on 1 ket, which gives me minus I 0 ket? Okay, so you, in a way, you can say Y gate on X, again it's kind of a rotation, and Y gate on 1, again it's kind of a rotation, right? Adding a relative phase and multiplying by some I is not going to make any difference, because when you are talking about a probability amplitude, let's say alpha is equal to I or minus I, the probability would be just equal to 1. Okay, so doesn't matter. Fine. Now let's go by X gate, Y gate, and Z gate are a kind of a rotation. Now, what about Hadamard gate? Hadamard gate acting on 0 gives me superposition. Okay, okay. So, what is its representation? Its action representation on, okay, right? So, on, let's say it's represent. Just a minute. Okay, let me take a new drawing. Yeah, 1 minute. Yes. Yeah. So Hadamard gate acting on 0 gives me equal superposition. So how should I represent that action on a block sphere? Interesting, right? So just take a block sphere again. Okay. X axis, Z gate, sorry, Z axis and axis. This is a block sphere for you. Initially, quantum state is along the X axis. Okay. Now it should become equally probable, 0 and 1. So anything other than north and south pole is a possible contributions comes from 0 ket and 1 ket. Okay, so when you try to rotate 0 ket, which is pointing along the the Z axis, let's say I'll rotate it by 90 degrees. Okay, pi by 2. Okay, so how did I do? I just take the vector pointing towards the Z axis, push that to connect and become along the X axis. Okay, so along the X axis it should point out. So I am rotating it by pi by 2 degrees. Okay, so if you do that, interestingly, you are going to get a equal superposition like this. How? Very simple. You go back and just recollect what is the quantum state representation in the first place, which is along the, as per the block sphere representation, it is cos theta by 2 0 ket plus sin theta by 2 exponential I phi, okay, 1 ket na, right? So here I am introducing theta is equal to pi by 2. When I introduce theta by pi by 2, let me write down explicitly, and I'll introduce phi is equal to 0. If you introduce it here, the quantum state I am going to get is cos theta by 2, theta is pi by 2 means cos pi by 4, which is 1 by square root of 2, 0 ket, x sin theta by 2 again 1 by square root of 2, exponential I0 is 1, so 1 ket. So I'm getting a equal proposition. So what I'm trying to do here is, when I introduce a pi by 2 pulse, if I have a pulse of photons, okay, a pulse of photons, there are so many photons inside. Okay, those photons are there coming and hitting an atom which is in the ground state. In the first place, it is going to go and interact with this atom and put the atom in a superposition. It will create this superposition, which is in fact rotating a quantum state vector from north pole to the horizontal equatorial plane along the x-axis. So in a mathematical terms or a quantum optics terms, the pulse which is going to be sent onto the atom is actually having area of the pulse. If you find out using some mathematics, it is called pi by 2 pulse. Okay, it is also called a pi pulse acting on the atom, creating a superposition. So if you just take any quantum gate, it is nothing but rotating the quantum state about some axis with some angle. Okay, so I can also rotate the quantum state from north pole, okay, from north pole to the equatorial plane along the y-axis. So the rotation is like this. Okay, remember, you have to confine yourself to either clockwise or anti-clockwise. You should not do either way. I'm just showing for the understanding here. Again, here also I'm rotating not by 180, probably it is by 270 degrees. Okay, 180 plus 90 degrees. If you do that, the vector goes down and then comes back and points along the y. So in this case, if you just see, right, what is the phi angle? Phi angle is actually 90 degrees, pi by 2. So corresponding to theta is equal to 270 degrees, phi is equal to pi by 2, you would get the equal superposition which is looking like this. Okay, so which is actually pointing along the y-axis in a y-axis in a block sphere. Okay, fine. So this we can somehow now conclude that all the quantum gates are simply rotations of a given quantum vector about some axis along some direction, from some direction to some other direction about some axis with some angle theta. So you can say that x gate is rotating about the x-axis with an angle what? Phi angle. It is rotating, and y gate is again, okay, rotating about some angle, right, and also inducing some phase. And z gate is not rotating, so RZ is not rotating, it is just inducing some phases. So, and H gate is rotating about either x axis with some angle, pi by 2 angle, or minus x axis, okay, minus x axis with some 2, uh, 2, okay, 3 pi by, so 3 pi by 2 or something like that, 3 pi by 2, something like that. You can figure it out. Okay, so conclusion is all the quantum gates are nothing but rotations about particular fixed axis. Okay, right? So we can, I think we started around 3 to 2:45. We can quickly take a break, right, and see. Wait a minute. If there are any questions. What about qubit positioned on the equatorial line? Right, it's up to you whether you start the initial state, right? That's a very interesting question somebody asked. If say, right, qubit is initially placed along the x-axis, which is what? It's equally superposition state, right? 0 plus 1. Okay, so this is the initial state I'm starting with. Now if the quantum state is pointing out, right, now if you just act x gate on that, x gate does what? X gate does 0 to 1, 1 to 0. Since they are equally probable, it is not going to make any probability interchange. So x gate has no effect, it remains the same. What about y gate? Y gate does both x plus z effect. So there is a probability amplitude remains the same, relative phase is added. Okay, so probably from this side, it may go to the negative x side when y gate is acted. Okay, so that is another rotation. Now, so it's all about on the equatorial plane, it is moving on with x and z or y. Okay, so now if you take a Hadamard gate, act on superposition, it's very interesting effect. Okay, so what I mean to say, let's say electron is being hopping in between. Now I'll send a pulse of photon. Okay, so what happens? Interestingly, if you just cross check, which is going to give me a single bit state. Okay, so in fact, this is actually led to something called reversibility in quantum states. Why? Because say let's say I start 0 ket, it becomes superposition. Okay, then I act again H on the superposition, I am getting 0. In fact, what it means? In fact, if I just take H, act H twice on a given quantum state, it is going to give me the same state. Beautiful, right? So the quantum gates are reversible in nature. What I mean is, if say there is a, let's say using a quantum gate, there is an input, there is an output, let's say, right? I understand that I don't want the output, I want to go back, so I can just send the information back and get back the old information. So that is actually reversible. You can prove, you take any gate, whether you take x you square, it is going to give me identity. You take y you square, it is going to give me identity. You take z you square, it's going to give me identity. H, it is going to give me identity. What it means, you take any gate operation or a quantum gate operation, act on a given quantum state, it is going to have no effect if I act twice. Okay, so that is what it's going to do. What about qubit positioned on equatorial uh, qubit gate positioned on equatorial? That's what I saw. Equatorial plane, I should told you that. Yeah, sphere is, this sphere is only used for single qubit gates or single qubit quantum representation. Okay, yeah, so we'll have a quick break, guys. Please take a 5 minutes break, and we'll start again at 3:55. Okay, Satyan sir, any problem with the audio?
No, sir, it is fine. So we can take a break.
Thank you, sir.
Yes.
Yeah, yeah. So once we come back, I'll show you this gate operations on IBM quantum experience.
Okay, sir.